Hello everyone, this is Solved by Hand channel. Welcome to the channel. Today we will solve a problem in fluid mechanics. So today we'll solve this problem. So we have fluid mechanics solved example 1. So this is the problem that we'll solve. The shear stress in a thin film of water. So this is the problem that we'll solve today. The shear stress in thin film of water. So this is the title of the problem that we'll solve today. The shear stress in a thin fluid of thin film of water. So the problem that we'll solve today is the shear stress in a thin film of water. It is a problem of fluid mechanics. So this is the problem that we will solve today. This is the figure of the problem, and this is the statement of the problem. The shear stress in a thin film of water. Let's read this together. The plate in a figure rests on the top of the film of water, which is at a temperature of 25 degrees Celsius. If a pressure difference occurs between A and B, so here we have A and here we have B. If pressure difference occurs between A and B and small force, so here we have small force, and the small force F is applied to the plate, the velocity profile across the thickness of the water can be described as U. This is U, which is the velocity. So the velocity profile across the thickness of the water can be described as U equal to 140 y minus 800 times y squared. The unit here is meter per second, where y is in meters. The problem that we have to solve, or the question that we have to answer, is determine the shear stress acting on a fixed surface and on the bottom of the plate. So let's look again at the figure of the problem. So here we have A and B between so the plate. So this is the plate. So this is plate, and this is the force applied F. So this is the plate, and this is the bottom of the moving plate. So this is the plate, and this is the bottom of the moving plate, and this is the fixed surface. So here we have the fixed surface, and here we have force F, which is applied on the moving plate. So this is the moving plate. So the force F is applied to the moving plate, and here this plate is fixed. So this plate is fixed. So the distance between the two plates is 10 millimeters. And here the force F, which is applied, to the moving plate. So the force which is applied to the moving plate is F. And here we have the velocity. So here what is vertical is the ordinate. So this is the ordinate, and U is the velocity. So U that we can see here, this is the velocity. So it's varying. So we can see the green allows. So the velocity between the two plates is varying. It is variable according to this equation. So U, which is the velocity, near the fixed surface, the velocity is 0. After that, the velocity, which has yellow, which has green arrows, the velocity is increasing. So near the fixed surface here, near the fixed surface, the velocity is 0. After that, we see that the velocity is increasing. So it is increasing according to these equations. U is equal 140 y. Y is the ordinate. So ordinate, or this vertical distance. So y is the vertical. For example, here y is 0, and here after that y is equal to 10 millimeters. So y is the vertical distance between the plates, between the fixed plate and the moving plate. So this is the fixed plate, or the fixed surface, and this is the moving plate, and y is the ordinate between them. So for example, at this point y has the value of 0, and for example at this point y has the value of 10 millimeters, and the velocity is shown by the green arrows. It increases. It is increasing according to this equation. u is equal 140 y minus 800 y squared, and the unit here is meter per second, because u is a velocity. It has the unit of meter per seconds, where y is in meters. So y is in meters. So the question or the problem that we have to solve, determine the shear stress acting on the fixed surface and on the bottom of the plate. So this is the question that we have to solve, or the problem that we have to solve. Determine the shear stress acting on the fixed surface. So this is the fixed surface. Determine the shear stress acting on the fixed surface and on the bottom of the plate. So fixed surface is this one. So this one, fixed surface, and on the bottom of the plate. So at the fixed surface and on the bottom of the plate. And this is the plate. This is the plate, and this is the bottom of this is the plate, and this is the bottom of the plate. And here we have fixed surface. Fixed surface. So let's try to solve this problem. So without any further delay, let's go to our paper and start moving our pen. Let's go to our paper. So a screen, show taskbar, and I will go to the paper. So this is the paper. Let's start writing. So the first thing that we have to write is Newton's laws of viscosity. We have to start by writing Newton's law of velocity. So Newton's law of viscosity So what does Newton's law of viscosity says? What does it say? So it says that tau, which is shear stress, is equal to, this is the diameter. I will name each one this after. So du that we see here is velocity, and here the ordinate. So let's explain each term in the equation. So tau is shear stress. The mu that we see here, mu is dynamic viscosity. And du that we see here is velocity. And y that we see here is the ordinate, or the vertical distance between the two plates. And if we take this term that we call, so I will take a different paper, different pen. So, and if we take this term which is between these two parentheses, so du, so the derivative of u with respect to y, so this term we call it the velocity gradient. So this is what we call the velocity gradient. So those are the terms that we have. So tau here is the shear stress, mu here is the dynamic viscosity, u that we see here is the velocity, and y that we see here is the ordinate. And the expression here, which is in between parentheses, which is the derivative of u with respect to y, this is what we call velocity gradient. So those are the terms that we need. So before solving, this is what we have. So the problem is, let's go back again to our problem. Problem say determine the shear stress acting on the fixed. So determine the shear stress. So we have to determine the shear stress. This is what we have to calculate. Determine the shear stress acting on the fixed surface, but on the bottom of the plate. We have to determine the shear stress. The shear stress is tau in the equation. So we have to determine to find the shear stress. So the shear stress. We have to determine the shear stress, which is this one. We have to determine tau. This is what we have to calculate in our problem. So let's continue with our problem. So we'll start with the dynamic viscosity. So in this equation we have seen that we need several terms. We need to calculate the dynamic viscosity, we need the velocity, we need the ordinate. So we have to find this and this and this in order to calculate tau, which is the shear stress. So we have to calculate the dynamic viscosity, we have to calculate the velocity, the derivative of it with respect to y. So we have to calculate all this term, this one, in order to calculate this, which is the shear stress. So let's continue. First, let's calculate the dynamic viscosity. So first of all, let's calculate the dynamic viscosity. So here we will continue dynamic viscosity. Dynamic viscosity. You have to calculate the dynamic viscosity. We can say that since water is a Newtonian fluid, this implies that Newton's law of viscosity applies. So since water is a Newtonian fluid, this means that Newton's laws of viscosity applies. So it means that we can use this equation. So since water is a Newtonian fluid, so Newton's laws of viscosity apply. So we can use this equation that we have used here. So we can use it. Because water is a Newtonian fluid, we can directly use this equation. So we have said that we have to calculate the dynamic viscosity. So we have water at 25 degrees Celsius. So at 25 degrees Celsius, because we have 25 degrees Celsius. I will go back. So here we have the temperature. The plate in the figure rests on the top of the thin film of water, which is at a temperature of 25 degrees Celsius. The plate in the figure rests on the top. So this is the plate. The plate in the figure rests on the top of the film of water, which is at a temperature of 25 degrees Celsius. The plate in the figure rests on the top of a thin film. So this is a thin film of water. The plate in the figure rests on the top of a thin film of water, which is a temperature of 25 degrees Celsius. So this thin film of water has a temperature of 25 degrees Celsius. So we have water and we have the temperature of water is 25 degrees Celsius. So we can directly use this table. So normally we find a table of this kind on any book of fluid mechanics. We can find tables of this. So it is named physical properties of water versus temperature. It is an SI unit. So we can use the table. We can use this table, physical properties of water versus temperature in SI unit. We have said that temperature is 25 degrees Celsius. So the temperature is 25. So accordingly we can take the value of the dynamic viscosity. We can so here For example, 25 degrees Celsius will give us, for the dynamic viscosity, it will give us 0.897 times 10 to the power 3. So at 25 degrees Celsius, the dynamic viscosity is 0.897 times 10 to the power 3, and the unit of the dynamic viscosity is newtons times second divided by meter squared. So let's write this. I will take this one. So let's go back to our paper. Let's go to our paper. So here, so let's write. So at T, which is the temperature, is equal to 25 degrees Celsius, we can, from the table that we have seen, we can extract a value for the dynamic viscosity. Mu is equal to, it will give us the value of 0.897 times 10 to the power 10 to the power minus 3, and the unit here is Newton times seconds divided by meter squared. So this is very important. So let's frame this value of dynamic viscosity. So this is very important for us. So let's frame it. So this is the dynamic viscosity. This is the value of the dynamic viscosity that we have seen. I will highlight it. So this is the value of the dynamic viscosity. Why we have calculated the dynamic of the value of the dynamic viscosity? Because we need it here. So the dynamic viscosity, the value of the dynamic viscosity, I will need it here. So I will need this in this equation. So I will need it in the Newton's law of viscosity. So because of that, first I have calculated mu, which is the dynamic viscosity. Why I have calculated? Because I will use it in this equation. So here we have mu in Newton's law of viscosity. So this is done. Let's continue to calculate the second term. The second term that we have to calculate is the velocity. So we have to calculate the velocity gradient. So we have to calculate this derivative of u, which is the velocity, with respect to the ordinate, which is y. So second, we have to calculate what we call the velocity gradient. So we have to calculate this term, the derivative of u, which is the velocity, with respect to y, which is the ordinate, or the vertical ordinate. So here we'll calculate this. We'll calculate this now. So let's continue. Now we'll calculate the velocity gradient. We calculate this, the velocity gradient. We will calculate it. I will write here velocity gradient. This is what I will calculate. So what we have for the speed. So what is the of the speed? So what we have for the speed? So for the speed, we have this equation. So for the speed, so because to calculate the velocity gradient, I need the velocity. I need an expression for the velocity. I need an expression for u. So u is the velocity. First, I need to find the expression for the velocity. So what is the expression for the velocity? Let's go back. So here, I will. So this is the expression of the velocity. I will need this expression. I will need this expression. So this is the expression of the velocity. I will use this one because here u, here is the velocity. It has the expression. So I will use this expression in order to calculate the velocity gradient. Use this expression for u. So I will use this expression. So in this expression we have u, which is the velocity, and we have y, which is the ordinate or the vertical distance between the two plates. So y that we see here is the ordinate. So it is the vertical distance between the two plates. So here the y, and here u, which is the speed. So u is represented by the green arrows. So this arrow and this arrow and this arrow and this arrow. If I take the variation of the arrows with respect to the ordinate, it will give me this equation. So I will use this equation. So let's go back again to our paper. Let's go to our paper. So for the velocity gradient, we will use this equation. U is equal to 40 times y minus 800 minus 800 times y squared, and the unit here is meter per second. So this I took it from the problem. So what I need? So I need the derivative of this with respect. So as I can see here in the equation. So what I need the velocity gradient. I need the velocity gradient. What is the meaning of velocity gradient? The meaning of the velocity gradient is the derivative of u with respect to y. So this is all that I need. I need velocity gradient. So what is the velocity gradient? The velocity gradient is the derivative of u with respect to y. This is what I need. So I need to derive u with respect to y. This is very simple mathematics. So that I will write here. So derivative of u with respect to this. I did mistake here. So I did the derivative of u with respect to y. So this is not included. So this is the derivative of with respect to y of this term, which is equal to 40 y minus 800 y squared. So this one is not included. This is just a mistake that I did. So I am eliminated. So this is just a mistake that I did. So I am here. And this one, the derivative of this one, and here the unit is meter per second. This it will give me, for the derivative, it will give me 40 minus 800, and the derivative of y squared, it will give me 2 times 1 y times 1 times 1. So times 1. If I calculate the derivative of, so here derivative of y to the power minus 2 is equal to times y y to the power 1 times the derivative of y, which is 1 that I can see here. So this one, if I simplify it, it will give me 40 minus 2 times 800, it will give me 1600 y, and the unit here, the unit will be second minus 1. So the unit here, second minus 1. So and if I look for the why we have here the unit of second minus 1, so why we have the unit of second minus 1, it is we write here that we have the unit here is second minus 1. Why? Because here it has units of 1 divided by meter. So this one, the derivative with respect to y has the unit of 1 over meter, 1 divided, or 1 over meter, and this one has the unit of meter per second. And if I multiply this one by this one, so we will have meter is cancelled with meter here because we have multiplication, and at the end we have the unit which is s second minus 1 or 1 over s. So here, because we have 1 over m times meter over second, and the meter here is cancelled with the meter here, and at the end we have the unit which is 1 over second, which is equal second minus 1. This is what we have here. This is what we have. So the unit here at the end is second minus 1, or 1 over second. So let's take another paper and write what we have found very clearly. So I will take another paper and I will write what we have found for the derivative of the speed, or what we have found for the velocity gradients. So for the velocity gradient, we have found that the u, this is u, du divided by dy is equal to 40 minus 1600 y, and the units that we found here is second minus 1. So this is what we found. I will frame it. So this is what we have found for, this is what we call velocity gradients. And this one is equal to the u over the y. This is just a correction of this one. This one is u. This is what we have found for the velocity gradients. So I will highlight it. So this is for the velocity gradients. So what else do we need to solve our problem? So what else do we need? So we needed y. So we needed an expression for y, for the dynamic viscosity. So for the mu, so for the dynamic viscosity, we found it. So for the dynamic viscosity, we found this. So for dynamic viscosity, we need also velocity gradient. We need also velocity gradient, which is the derivative of u, which is the velocity with respect to y. We need it also. We have found it. So this is the velocity gradient. So what else do we need in order to solve our problem about shear stress? We need only to do the calculation. So we need only to perform the calculation. I will continue our problem. So we have to determine the shear stress acting on the fixed surface and on the bottom of the plate. So we have to determine the shear stress at two places, or at two locations. Location number one on the fixed surface. So we have to calculate the shear stress on the fixed surface. This is location 1. Location 2 is the bottom of the plate. See, the bottom of the plate. So determine the shear stress acting on the fixed surface. So this is the fixed surface. We have to determine the shear stress acting on the fixed surface here, and and on the bottom of the plate. On the bottom of the plate means here at this location. On the bottom of the plate, this is the plate. So this is the plate, and this is the bottom of the plate. So we have to calculate the shear stress at two locations. Location number one on the fixed surface. So this is the fixed surface. This is location one, and we have to calculate the shear stress also. This is stress also on the bottom of the plate. So this is the plate. So this is the plate, and this is the bottom. This is the bottom. So we have to calculate the shear stress here at the bottom of the plate, and also here near the fixed surface. Near the fixed surface. So now, let's start by the fixed surface. So we'll start by calculating the shear stress near the fixed surface. I will start by calculating the shear stress near the fixed surface. I will calculate it here. So let's go to our paper. So that's that. So here. So for example, at shear stress at the fixed surface. So we will calculate the value of the shear stress at the fixed surface. We will use these equations. We'll use this equation. We'll use this equation. Tau is equal mu times the derivative of u with respect to y. So we'll use this equation. Tau is equal to mu times the derivative of u with respect to y, which is tau is equal to the dynamic viscosity times the derivative of velocity with respect of the ordinate. So we can use tau, which is the shear stress, is equal to the dynamic viscosity times the derivative of the velocity, which is u, with respect to y, which is the ordinate. So we will use this equation in order to calculate the shear stress. We will use this equation. We'll use this equation. So here we have tau is equal to mu times the derivative of u with respect to y. This as at y equal to 0. Why do we have y is equal to 0? Why do we use y is equal to 0? Because of this. So because here we are at the fixed surface. Here we are at the fixed surface. So what is the value of y near the fixed surface? Let's go to the figure. So here we are near the fixed surface. So this is the fixed surface. What is the value of y near the fixed surface? Is equal to 0. So here, because we can see the axis of y, so near the fixed surface here, y is equal to 0. It starts from 0 and it starts increasing. So here, the value of y, which is, because here we have the axis of yu, so this is the origin of the axis. So near the fixed surface here, so here, near the fixed surface, y is equal to 0. So here, y is equal to 0. Let's go to our paper. So we have said that we have y equal to 0 near the fixed surface. This one will give me, I will take the value of mu, which is the dynamic viscosity. What is the value of mu? It has this value. It has this value. 0.897 times 10 to the power 3 Newton times second per meter squared. So this is the value of u. So because here I need the value of u, I need it. So I need the value of mu. I need the value of mu here. What is the value of mu? So the value of mu, I will take it from this one. We have found it in the table for the temperature of 25 degrees Celsius. We have found it for 25 degrees Celsius. So the value of mu is this one, 0.897 times 10 to the power 3 newtons times second per meter squared. So we'll take the value. I will continue. So here is equal to 0.897 times 10 to the power 3, and the unit here is Newton times second
per meter squared.
squared.
This
one.
So
So this is just mu times the derivative of u with respect to y at y equal to 0. So the derivative of u with respect to y, derivative of u with respect to y at y equals 0, which means that in these equations, so this is the expression for the, this is what we have found for the derivative of u with respect to y. We have found this one. We have found this one. So we have found this. So the derivative of u with respect to y, we have found this expression. I will replace the expression here. So we have found this expression. So I will replace this expression here. It will give me 40 minus 106 y, and the unit here, of course, is second minus 1. So what I have to do here is to replace by y is equal to 0. So here we have y equal to 0, so I will replace this y here. It will be equal to 0. And this will give me is equal to 0.897 times 10 to the power 3 Newton times second per meter squared times, it will give me here 40 minus 0, second minus 1, second minus 1. And at the end, finally, this will give me, at the end, it will give me tau, that we are looking for. Tau is equal to 35. If you do the calculation between here and here, you have here 40. It will give me 35.88 10 times 10 to the power 3. And the unit here, so we have here for the units Newton second per meter squared, and here we have unit s minus 1, which is 1 over s. Then we have this unit, so it's called this one is cancelled with this one, and it will give me for the units, it will give me Newton over meter squared. So this is the value of tau. So this is what we have found. So this is what we found for the shear stress at the fixed surface. So this is the shear stress at fixed surface. This is the shear stress at the fixed surface. Now let's continue with our problem. So this is at the fixed surface. We found this value. We found this value for the shear stress at the fixed surface. Let's continue for at the bottom of the moving plate. So let's go to our problem. So this is our problem, and this is the question that we have to solve. Determine the shear stress acting on the fixed surface. we have already solved that. Determine the shear stress acting on the fixed surface. We have already solved that. What is remaining for us is to determine the shear stress at the bottom of the plate, which means that we have to determine the shear stress at the bottom of the plate, which means we have to determine the shear stress here. This is the plate, and this is the bottom of the plate. So determine the shear stress on the bottom of the plate. So here we have to calculate. We have already calculated the shear stress near the fixed surface. We have calculated. It gives us the value of 35 times 35.88 times 10 to the power minus 3 Newton per meter squared. So we have calculated the shear stress near on the fixed surface. We have already calculated it. Now we have to calculate the shear stress near the bottom of the plate. We have to calculate this. We have to calculate the shear stress at the bottom of the plate. On the bottom of the plate. So this is the plate. This is plate. This is the bottom of the plate. So we have to calculate the shear stress here. Here. And of course, what is the value of y here? So here the value of here is equal to 10 millimeters. So for here, so near the on the fixed surface, y was equal to 0. Now we have to calculate the shear stress at the bottom of the plate. And what is the value of y here? So what is the value of y here? Near the bottom, the value of y is equal to 10 millimeters. 10 millimeters. So we have to calculate the value of y. Or the ordinate y is here near the bottom of the plate. Yes, this is the bottom of the plate. So the value near the bottom of the plate is equal to y. So here y is equal to 10 millimeters. So let's apply this. So here y is equal to 10 millimeters. So let's go back to our paper. So let's go to our paper. So let's calculate shear stress at bottom
of
the moving plate. So at the bottom of the moving plate. So at shear stress at the bottom of the moving plate. So at the bottom of the moving plate we have y is equal to 10 millimeters, and it is equal to 0.01 meter. So we have to use this. So it will give me O, which is the shear stress that I want to calculate, is equal to mu times the derivative of the speed with respect to y, which is the ordinate, at y at y equal to 0.01 meter. So here. So we have here. So here we have y equal 0.01 meter, and here also we have y equal to 0.01 meter. Let's continue with our calculation. So we have found tau is equal to mu times the derivative of u with respect to y at y equal to 0.01 meter. Why 0.01? Because we are at the bottom of the moving plate. So at the bottom of the moving plate we have at the bottom of the moving plate we have y is equal to 10 millimeter, which is equal to 0.01 meter. So at the bottom of the plate we have y equal to 10 millimeter, which is equal to 0.01 meter. So because of that we use here 0.01 meter. So this will give me. So I need value of mu. So here I need value of of me, which is the dynamic viscosity. So I will use this value.
I will use this
I will
value
use this value for me. So I will use this value for the dynamic viscosity, which is equal to 0.897 times 10 to the power minus 3 Newton times second per meter squared. So I will use this value for mu, so for the dynamic viscosity. So I will use it here. It will give me equal to 0.897 times 10 to the power minus 3, and the unit here is, so I will open bracket here. The Newton here, the unit here is Newton times second over meter squared times, so, and I have to use these equations, the equation that we have found for the velocity gradients. So for the velocity gradients, we have found this equation. So for the velocity gradient, we have found this equation. It is equal to 40 minus 1600 y. So it is equal to 40 minus, I will use the same equation here. I will use this equation, 40 minus 1600 y, and the unit is second minus 1. So I will use this. So I will use this one. It will give me 40 minus 1600 y, and the unit here, it will be second minus 1. So, and I have to replace for the y here, since we are working with at y, near the bottom of the moving plate. So we are near the bottom of the moving plate. So we are at y is equal to 0.01 meters. So I have to replace this y here that I can see here by 0. I will give it the value of 0.01. So I have to give the value to the value that I have to give to y here is 0.01 meters. So I have to give it here. So, and after the calculation, it will give me that tau is equal to I will keep the same equation. So 0.897 times 10 to the power minus 3 Newton second over meter squared times 40 minus 1600, and I will have to replace y by 0.01. So 0.01 meter. I will give it the value of meter. Yes. And here I have to keep second minus 1. So, and at the end, it will give me this value. At the end, I will have this value. So tau is equal to is equal to 21. So after calculation every time, it will give me 21 times 5 millipascal. So I will frame this. So this brings us to the end of this video. So we have calculated the shear stress at fixed surface. So we have calculated the shear stress at fixed surface. We have calculated it. We have calculated the shear stress at fixed surface. We have found for this value that this value of tau, so tau is shear stress is equal to 35 times 88 times 10 to the power minus 3 Newton per meter squared. So you have found this value. And for the shear stress at the bottom of the moving plate, so for the shear stress at the bottom of the moving plate, which means that at y equal to 10 millimeters or 0.01 meters. So for this value, we have found that for the shear stress, we have found this value, which is equal to 21 minus 21.5 millipascal. So we have here we have found for the shear stress that tau is equal to 21.5 millipascal. Or this one is also equal to 21.5 10 to the power minus 3 Pascal is equal to 21.5 10 to the power minus 3 Newton per meter squared. So all of them. So here the unit is millipascal, and here the unit is Pascal, and here the unit is Newton per meter squared. So this is all for this problem that we have just solved. So this finishes this problem. I will go back again to the presentation. So we have solved this problem. This problem was about the shear stress in the fin from water. So we were having two plates, one moving plate, and we were also having another fixed plate. So we had a fixed plate and we have a moving plate, and we have calculated the shear stress between them. So we have calculated the shear stress at the bottom of the moving plate, which means here for y is equal to 10 millimeter, and here we have calculated also the shear stress for near the fixed plate, which means we have calculated the shear stress for y equal to 0. We have found the two expressions. We have also used this table to find the dynamic viscosity of water. So in order to calculate the dynamic viscosity of water at 25 degrees Celsius, we have used this table, and we have found that for 25 degrees Celsius, the value of the dynamic viscosity mu is equal to 0.897 times 10 to the power minus 3 Newton times seconds per meter squared. And we have used it to calculate the dynamic viscosity that we have used in our exercise. So this is the end of this problem. I hope that we have understood everything that we have seen today while solving this problem. See you in another problem. Thank you very much. See you next time, and take care of yourself. Bye bye.